Welcome to module 3. In this module we will be looking at OS management services. What is it that the OS need to manage? A OS is a layer which tries to help the CPU and the application software to work and get the required services. So, OS is basically a service layer. It services the application software, it satisfies the needs of the application software by getting whatever the application software wants executed on the hardware. And so, what is it, what sort of services will the application layer need from the hardware, and how does the operating system basically handles them? This is something very crucial for us to understand, because the understanding of this will help us in understanding the information security part of building an operating system. Many of the vulnerabilities come because these interfaces are not well understood either by the application software or by the operating system module, and because of this lacuna or whatever, a gap in understanding the functionalities, the vulnerabilities basically creep in. Now, let us understand the first most important functionality of an operating system is process management. What is a process? Already I said a process is a program in execution. There can be variety of processes. What you see on a mobile phone is actually an interactive process. It is actually a time shared process. A process can also be that I submit and sometime later it gets executed. This is called a batch job. So, you submit it and tomorrow morning you come and see whether it is done. This basically happens on large supercomputing, high performance computing environments, where you do not talk to the system that is executing a program one to one, like how do you talk to your laptop or your mobile phone or your desktop, but you actually submit the program, and over a period of time the program actually gets executed, and say within some reasonable amount of time the results come up. Okay. So, this is basically called a batch job. A time shared job is something that we do here, where there are many processes executing on a system, and your CPU is time shared between multiple of them. And then there are other type of processes which we need to understand here, is called a system task. A system task is different from a user task. When I execute a program, then it is a user program, but when we go and do some important functionalities, for example, I go and say printf or scanf, then it basically calls the system for help, because I as a say for example I as a hello world program will not know how to go and print on the screen, because I do not know what screen is there. So, I basically use that printf routine, and that printf routine essentially calls the operating system, which in turn calls the graphics adapter, and there is a sequence of calls that go before the hello world appears on the screen, right. So, this is very important. So, when we look at process, there could be time shared interactive processes, there could be batch processes, and more importantly there is another category of process which is called system task, which works at a higher privilege level. Now, when we want to execute a process, again I have covered this in great detail in the information security 2 course. When I want to execute a process, I go and ask the operating system, say I am a process, I have say 1 megabyte of code, and I need say half a megabyte of data, I have so many arrays, I have so many things, so give me the storage. So, first the operating system has to give you some memory where the process can be loaded, the data etc. can be loaded. After that we start executing this. So, every process will need certain resources in terms of CPU time, because I need to execute the program, I need some amount of memory, then I would like to do some IO in like printf and scanf from the keyboard and printf on the screen. I would also try and do lot of fprintf and fscanf. I am using C language to basically explain this. I hope all of you know C. If you do not know, just get to know these commands. So, I use fscanf and fprintf to read and write from files. So, as a process I need lot of resources including CPU time, memory, files, IO devices to complete my task or to accomplish my task, and these resources are made available to the process through the operating system, and whenever the process completes, then it returns back the resources to the operating system. So, the operating system, one of the important aspects of process management is for the operating system to provide CPU time to provide memory, files, IO devices, etc. The second important process management is to actually monitor and control the execution of a process. When we say, suppose we compile a C program and say ./a.out and press the enter, now a process has to be created. When the process completes, it needs to be deleted. So there is something called a process creation and deletion, and we can also suspend a process and make it wait. So process suspension, and once a suspended process I want to bring it back, I can again revoke it back, or what you call as process resumption. So this is also operating system functionality. Why, as I mentioned earlier, why should a process get suspended? A process actually gets suspended because it is waiting for an IO operation to complete. And why should it get resumed? After the, or when will it get resumed? After the IO completes, it can basically resume. So there is a provision of mechanisms for process synchronization and process communication. That is very, very important. What do you mean by process synchronization? I want to perform a synchronous IO. This is an example for a process synchronization. And one process wants to communicate to another process. So I could have inter-process communication, and we even within a process, one subroutine wants to pass information to another subroutine. There is also intra-process communication that happens between different modules of a given program. Now, we are also talking of sharing a CPU. What do you mean by sharing a CPU? Today programs can also be multi-threaded. Thread is nothing but a unit of execution. So instead of one unit of execution running, I could have 4 units of execution running, right? So this is called a multi-threaded program, where each thread can execute concurrently without depending on the another thread. So if I have some certain operations that could be concurrently executed, I go to a multi-threaded system and say, suppose I have 4 different operations that could execute concurrently. I go to a multi-threaded system which has 4 threads and give one operation each to one of these threads, and all the 4 can happen concurrently. If I do not have a threaded architecture, then these 4 operations have to happen one after another. So a multi-threaded architecture gives us very, very good speed up or throughput. So if I have a single threaded process in which I am using only one thread, then there will be one program counter which basically specifies the location of the next instruction. But if I have multi-threaded process, each of the multi-threaded process has one program counter. Each thread has a program counter. So now when I look at a multi-threaded architecture, an architecture that could execute more than one thread at a time, now the operating system's responsibility is to see that these program counters are handled properly, and the processes are moving in and out properly. So there is a lot of difference between having a single threaded system versus a multi-threaded system, and the process management accordingly changes. Now many of the security vulnerabilities come by the way why different threads actually interact with each other, and that needs to also be taken care of. So when you look at the information security 2 course, there we have introduced a notion of what we call as call gate towards the end of those lectures, which basically talks about multi-layer security. So and many of these vulnerabilities actually happen when we switch from one mode or one unit of execution to another unit of execution. It can be from one program to another program, and when we do this switching, the isolation between these 2 programs is not so perfect, and because of that lack of isolation, some information of program 1, when it switches to program, when the CPU switches from program 1 to program 2, some information of program 1 can be leaked on to program 2, and that forms a very, very important aspect of information security. So to finally conclude, process management is responsible for creating and deleting both user and system processes. So now we are making a distinction between what is a user process. For example, the hello world program is a user process, but the printf and the subsequent execution that is happening is a system process. So that is how we can distinguish very quickly between the user and system processes. And the operating system is also responsible for suspending and resuming processes. It also provides mechanisms for process synchronization. It will also provide mechanisms for process communication, and it also is useful for handling what we call as deadlock. What is a deadlock? Deadlock is nothing but a process P1 is waiting for a resource R1 which is currently held by process P2 which in turn is waiting for a resource R2 which is held by process P1. So P1 wants R1 which is held by P2 which needs R2 which is held by P1. So for P1 to complete it needs R1, it has R2 with it, and for P2 to complete it needs R2 and it has R1 with it. So each of them are competing, and so this is basically what we call as a deadlock, and the process operating system should handle deadlocks. The next important aspect of an operating system is to basically handle memory. Memory is a very large array of words, each with its own address. And what do we store in memory? We store a lot of data that are basically shared that are used by the CPU, and also basically that are shared between the CPU and the I/O devices. We already mentioned the notion of what we call as a direct memory access, wherein a peripheral can write directly into a memory location and then the CPU can later read from that memory location. So when we look at the operating system's role in memory management, it has to provide the necessary memory that is needed by a particular process, and in the case where we have a notion of virtual memory, the operating system can go and it has to go and set up certain paging related or whatever the virtual memory related stuff, and then it has to basically give those memory to the respective process. So memory management is also covered, especially the virtual memory, setting up page tables, etc., and segmentation. These are all covered. There are very interesting lab exercises that have been given as part of Information Security 2 course. I advise you to go and look at that in greater detail. So the operating system is responsible for giving memory to a process, and it is also responsible for getting back that memory and releasing it properly so that it can be used by another process at some other later point of time. So space or memory management is very, very important, and there are two aspects of memory management. One is memory allocation and release of memory, and handling which part of the memory is allocated, which is not allocated, etc. The second part of memory management is also to look at provision of a virtual memory. So every program assumes that it has 4 GB RAM, but I could have only 4 GB RAM in the system, and there could be hundreds of processes that are sharing this. So a notion of virtual memory basically helps you in realizing that all the memory is given to a particular process in terms of virtually. So there will be 100 processes, but each process thinks that the entire 4 GB address space is for it, which will not necessarily be the case, but the operating system will give you that virtual feeling. And importantly, when a process completes or when a resource is released, it has to be properly documented, or it has to be properly maintained so that it goes and it could be reused at a later stage. Note that a file is the most visible component of operating system. Anything that I store, the basic unit of information is called file, and it's actually a logical storage unit, and file gives you an abstraction. So today I created this PPT file in another desktop, then I sent it through an email, somebody copied it and they have stored it in a desktop, and now they brought it here. So this file is called module3.ppt, right? But the way the same module3.ppt was there in my disk, then it was there on my mail server, then it came to the desktop of Benjamin here. Benjamin is the staff who is helping me in recording this lecture, and then from there he transformed to put it into this laptop. So but the file has remained the same, but the way it is getting stored, it got stored in my desktop, which is a Mac Apple system, and then the way it got stored in the mail server, we do not know how the mail server is configured, it is some other disk. The way it got stored in the studio and the way it is stored on the laptop, they are all different disks, different formats, but a file remains as a file from the user's perspective. I just see module3.ppt everywhere, right? So that is very, very important, and who takes care of this uniform view for the user, though the way it is stored is different, the operating system uses that. So that is very, very important here, and the operating system is responsible for the following activities in connection with file management: creating a file, deleting a file, creating a directory, deleting a directory, and support of primitives for manipulating files and directories, right? Deleting a file, so changing some permissions, etc., etc. And then the most important thing is we need to map the files onto the secondary storage. and then we have to do file backup on stable non-volatile storage media, so that for archival purpose and retrieval purpose in case there is a power breakdown, etc. So, these are all very important aspects of file management. In addition, there is something called a secondary storage management. What is a secondary storage? The main storage is called, or whatever called as a primary storage, is basically the main memory. A secondary storage is a system, is the hard disk for example, or it can be any even online storage medium. Today I could go Dropbox, etc. So, these are all secondary storage for us. So, one of the important thing with respect to a disk, for example, the operating system is responsible for the following activities in connection with managing a disk, for example in hard disk. Now, the operating system has to maintain the complete thing about the free space that is available there. So, I want to store a file, I should know which space is free in the disk. So, this is what we call as free space management, and then I have to, there are so many free space, I have to allocate a particular space, that is called storage allocation, and then every time I read or write from the disk. Now, this today we are looking at SSDs or solid state devices, but in olden days when they look at mechanical disks, right, then the head will be at some point, and if there are 10 files, I would like to take that file which is very close to the head, so that quickly I can write it there. So, I will decide on which file to be written at which point of time, I in the sense the operating system. So, the disk scheduling also becomes a very important part of secondary storage management by the operating system. Now there is something called the IO system management. IO system management is that I have an IO device that is trying to communicate with the CPU, and how do we go about doing this? So, what is it for me to read from an IO device? First thing is I need to understand how I can talk with the IO device. I means the CPU. Now, there are hundreds of IO devices in the market, and all of them are compatible with the current the Windows or the Unix operating system. They are compatible with it. Now, how does this compatibility come? How are you able to access n number of peripherals here? The reason is that there is a driver, a software which talks to the corresponding device controller. Told you in the previous module that every peripheral will come with a peripheral controller. Disk comes with a disk controller, graphics card comes with a graphics card controller. Now, there is a peripheral and there is a hardware which controls that peripheral, and that hardware is interfaced to the CPU through the bus. Now, what is the next step here? Now, the next step here is that somebody has to talk to that controller, and who is that somebody? It is the operating system. Which part of the operating system? That is called a device driver. So, the moment you insert some USB device, then immediately into your system, either it is a Windows or Linux, then immediately it says we are trying to find out and install a device driver. So, the device driver talks to the device controller, and then in turn it will go and access the device controller will access the device and do the necessary job. So, and please note that the IO system is much slower than the actual CPU, and so what we do is that as and when we read from that, we buffer the inputs and the outputs if we are going to write into a location. So, we do that buffering to actually match the speed, right. So, when we look at IO systems, one of the most important thing is to have a buffer caching system. Now, a buffer caching system basically brings from a disk some data and it stores in the memory and it keeps as a cache. Now, improper handling of the security of the buffer cache can essentially lead to information leakage, right. As a process A would have some confidential data on the disk which is basically taken up and put it in the buffer cache, and then the process A completes, but the buffer cache is not erased, it is just in a free list, and so the next process can come and look at this buffer cache and try to get lot more information about the password, etc., or anything there. So, handling this buffer caching system is very important from a security perspective, and there is also something called memory management of IO, and there looking at the caching, looking at what we call as spooling, which is nothing but the overlapping of output of one job with the input of IO including of others jobs. So, this is also very important. So, the memory management of I/O, the I/O system itself is very crucial for the operating system. And so what the operating system today provides for handling I/O system is a general device driver interface, and I already explained what a device driver is. And we also need these drivers for multiple type of hardwares that we use. So an operating system, why we need a generic device driver interface? Because we have thousands of peripherals that we could attach to the different systems, and so the drivers need to have a generic device driver interface. We have already explained what is caching, but I will just quickly touch here. Caching is nothing but between two levels of storage in the storage hierarchy. The slower device, when it tries to interface to the faster device, has caching mechanism built in the faster device, so that every time I want to go and access a data, I need not go to the slower device, but I could have it from the faster device. So this is the notion of what we call as cache. And the notion of cache actually works because programmers, when they write a program, implicitly follow, it is not intentional, but it implicitly follows two important things called locality of reference. One is called spatial locality, another is called temporal locality. What is spatial locality? If I address data, if I go and access data or instruction at address A, within the next few milliseconds I will access something at the path A plus delta A. So when I am fetching address A, I will also fetch all the things around it, so that next time I need not go to the disk, but I can take it from the cache. Bring it means bring it where? Bring and store it in the cache, and I could access the cache at a later time. Another locality of reference called temporal locality, which basically talks about I access a data at time t, the probability that I will be accessing the data at time t plus delta t is very high. For example, I initialize a variable before I use it. So initialization is one access to the variable, and immediately after that I start using that variable, I write into the variable or read from that variable. So this is an example. So the way a programmer's mind works automatically resolves into what we call as the temporal and spatial locality of reference. So when I access an address A at time t, probability that I will access A at time t plus delta t is very high. The probability that I will access an address very close to A in the next delta t time is also very high, and this makes caching very important aspect. The next aspect of operating system that we need to talk about is the distributed system. What do you mean by a distributed system? You have multiple computers connected, there is nothing that they share except that they are connected through a cable or what we call as a communication network. Now we need to program this. So let me say I have thousands of such computers networked, and now I have a job which has 1000 parts, and each of these parts can execute concurrently. Now I need a mechanism by which I can take my job and split it up into those 1000 small parts and allocate one part each to one of these processes. They execute and then they communicate and then they solve the problem. So this is basically called a distributed system, and the most crucial thing for a distributed system is to have a very high speed interconnection network by which one system can talk to another. So networking actually comes in here with great. So networking is not to connect two remote systems, but today networking plays a crucial role in building of many of these supercomputers, wherein one processor gets connected to another processor through a network stack. So that notion of distributed systems is very important. The other thing is that I need to manage the operating system by giving command. So a lot of people would have known what a command prompt is. As a part of this course, as we proceed, we will also talk much more about commands, the terminal, where many commands will also be taught as a part of this course. Now what is a command? A command is basically that to create a file, to delete a file, to do a IO, or to access main memory, to access secondary storage system, to create some for protection environment. I can also do certain execute certain network commands through the command interpretation. So there is a command line interpreter both for Unix, which is called a shell, a bash shell, etc., and for Windows there is command always. So this command is basically an interpretation. What is an interpretation? So I have say 10 commands. An interpreter will take one command, execute it, then take the next command and execute it. A compiler will compile all the 10 commands and execute it in one shot. So there is a difference between an interpreter and a compiler. So the command is always interpreted, in the sense one command is taken, it is executed, then the next command, then the next command. That is why we call it as command interpretation here. We strongly urge you to go and look at the command in Windows or the Linux system, terminal in the Linux system, and understand some of the popular commands or very effective or very heavily used commands in the respective operating systems. Now, we will also define what we mean by protection and what we mean by security. Protection is something which is very internal to the system. We will talk about protection in more detail as we go into the next module, but as far as this module is concerned, please understand that within a system I need to protect lot of things. What are the things we will see in the next module, but some sort of ensuring security within the system is called protection. Protection mechanism involved to protect a system from outside, that is basically called security. Security is the defense of the system against internal and external attacks. Okay. So, the internal attack is somebody comes and hacks your password internally, and then it can do that, and an external attack could be something like a denial of service, it can be worms, viruses, etc. So, the protection and security is basically employed at 3 different levels. First, if you take the operating system, the Unix operating system, it has 2 levels of protection. First, there is an user ID, then there is an user ID and the group ID put together will give you another protection. So, for a particular file, there will be a owner who has some permissions for it, then that owner can belong to a group, and that any member of that group will have some permission on it, and then you will have anybody else. So, for every entity there is a way by which I could create certain access rights for certain people or certain users by which I can ensure both protection and security. So, protection is internal threats between the modules, and security is external threat to the system. Why do we need to protect? I need to protect because today let us take a mail server as big as a Google server, Gmail server. Now, if I go and do some fault on that and the entire server stops, it essentially means there is a denial of service to the entire mail users, say millions or billions of users of Gmail, right. So, that is very important. So, one of the important thing is that I need to protect my data from other programs which are trying to access it. I need to protect processes from doing some illegal operation which will go and create chaos for the other processes. So, there is a need to protect the program itself, and there is also a need to protect this program from going and doing something which it should not do in the context of another process. So, there is an intra-process protection and an inter-process protection that we need to take around, and this is very important from an information security point of view. So, we will continue about security measures in the next module. Thank you.